Well, good afternoon to you all, and I would like to thank the organizers for inviting me to give this talk this afternoon. Well, as you know, of course, plate tectonics was born from the ocean. That was very obvious this morning. But we field geologists, we worked on the continents, although we sometimes go on ship because some of the truth is off the coast, but most of our time is spent in the continent on mountain belts or rift zone, deformation zones in general. So, and plate tectonics is nowadays a consensus, and it is a framework of all what we do on continents. Very soon after the proposition of the plate tectonic theory, the geologists jumped on the idea, and they explain the formation of mountain belts with interaction between plates, of course, and interaction between continents. And this very famous paper by Dewey and Bird as soon as 1970 is the paper I would have dreamed to write, but unfortunately I was much too young at that time. And also this paper by Molnar and Taponnier is also very famous with the India-Asia collision. I'm sorry, the definition is not very good. And there is these images we saw also this morning about mantle convection, because before plate tectonics, some geologists like Arthur Holmes and David Griggs and others tried to propose that some of the deformation we see, and most of the deformation we see on the continent are due to mantle convection. But the connection between the two approaches was not done. And there is still a debate among us between those who think that everything is due to plate interactions, or continent interaction in that case, and those who think that mantle convection plays a major role not only in displacing plates, but in deforming them. Okay? And that's what I'll be talking about. So plate kinematics is the framework for studying crustal deformation, and I'll be talking mostly about long-term deformation here, mountain belt rifts, and I will use three examples. One is the Mediterranean region, the second one is the Middle East, and the third one, I hope I will have time, is East Asia and the India-Asia collision. So let's start with the Mediterranean, which is very often presented as a landlocked basin. So during the last 35 million years, mountain belts formed in the Mediterranean region within the interaction zone between Africa and Eurasia, at the same time as back-arc basins opened. Okay, in the Neogene, for instance, the Nigro-Provençal basin here, or the Tyrrhenian Sea, the Aegean Sea formed at the same time as mountain belts such as the Apennines or the Maghrebides here, the Betty Cordillera formed here. So how is this possible? So let's start with the eastern part of it, the Anatolian Aegean region. I will concentrate mainly on it. You see on this reconstruction here, on this north-south section, that you see the ages here. From the late Cretaceous to the present, you see that we start with the formation of a mountain belt, crustal thickening here, and then from 35 MA, the subduction zone starts to retreat here, and the mountain belt that has been formed before suddenly is extended, and everything collapses, and metamorphic complexes are exhumed. They are the pinkish stuff here. Okay, so before you get too tired with this movie, which is too fast, move to another one. So at the scale of the Mediterranean, here you see these back-arc basins opening behind the retreating slabs here, and the Aegean Sea, the Tyrrhenian Sea. And what's very obvious on this reconstruction, but could be seen also on a picture showing the GPS velocity field in that area, is that the long-term displacement, the displacement within the Mediterranean here, are faster than the Africa-Eurasia convergence. It's even more obvious with the GPS velocity field, but if you look here, for instance, in that area, the opening of the Southern Tyrrhenian Sea here was achieved at more than 10 centimeters per year, which is much, much faster than the Africa-Eurasia convergence here. So the convergence is thus not the only engine of deformation in the Mediterranean, and slab dynamics is the most efficient of engines here. So extension in that area, in the Aegean Sea, is accommodated by large-scale, low-angle normal fault. You have here the NCDS, the North Cycladic Detachment System, here, and shear zones. And we'll come back to the sense of shear in this shear zone later on. You see that all the arrows are pointing toward the north here. So let's focus for a few examples on the island of Tinos here. You see not a bad place to work. And you see here the North Cycladic Detachment System here on Tinos Island, separating an upper unit that has never seen the high-pressure metamorphism here from a low unit here, which is the cycladic blue schist, are very famous for the blue schist and the eclogite. And the normal fault runs just below them. Okay? And this small fault here actually is not small at all. It has accommodated at least 70 kilometers of normal sense displacement, maybe 100. Okay. Another view of this detachment here. So the fault is running here between this upper unit and the cycladic blue schist over here. And if we focus on this point here, you see here some of the faults. It's not a single fault, it's several faults. And you see the kinematic criteria showing the sense of shear toward the northeast, which is a low-angle normal fault displacement here. Another very spectacular example is Mykonos, not far from Tinos here. And you see here the detachment, the shear zone below, that's the Mykonos granite here, and late Miocene sediments offset with a steeply dipping normal fault that roots on the detachment. Okay, so they are all very spectacular. If now we try to understand, to look at the deformation deeper, that's in the mantle. So the best tool to work on mantle deformation is probably seismic anisotropy here. And you have here the bars with different colors, shows you the direction that we could take as a direction of stretching in the mantle, probably shearing in the mantle. And if we focus on this area where we have back-arc basin, and we have lower crustal material exhumed at the surface in the metamorphic core complexes and detachments, the Aegean Sea, the Northern Tyrrhenian Sea, and the Alboran Sea region, what we see is that the mantle strain, if you like, mimics that of the crust here. And this suggests a very strong coupling between flow in the mantle or shearing in the mantle and deformation in the crust. On these reconstructions here, you see the evolution of that same area from the closure of the Tethys Ocean and then the migration of the subduction zone here toward the south here, and the exhumation of various core complexes, the magmatism, and so on. And you see also the propagation of this large North Anatolian fault here. So if we look at the motion path on these reconstructions here, you see the displacement toward the south here. You see very well the rotation. And what is quite obvious also is the difference between the quantity of displacement here in the east and in the western part of Turkey, in the Menderes Massif, and here in the eastern part of the Aegean Sea. And this big difference here is accommodated by a quite wide accommodation zone here. And the difference between this zone here and this here is accommodated by this differential rotation of the Helenide here, shown very well by paleomagnetism here. Okay. So this differential motion between the Aegean domain and Anatolia through time is mostly the consequence of a tear here in the subducting Hellenic slab. And this part of the tear of the slab here behaves independently from this part here. And this tear is very well imaged now by seismic tomography. You see this seismic model here by Biriol and others in 2011. And the tear is very visible in any sort of tomographic model here. Okay. So the geometry of subducting lithosphere in the Mediterranean Sea is quite well imaged now. That's another example in the western part of the Mediterranean here. You see the slab below the Gibraltar Arc, or here below Calabria here. And what we can do, for the sake of simplicity, is just draw a cartoon of the geometry of these slabs here. So this is not geophysics, it's just hand drawing by myself. So you see the main structures at the surface here. So I remove the topography, I remove the structures, and you see what remains is the geometry of the African slab below the Mediterranean region. That's the European slab below the Alps and the Carpathians here. Okay? You see that the geometry is complex, and you have detached pieces of slabs here. You have holes forming within the slab. You have almost no slab remaining below Anatolia here, and you have tears within the slab. This one is below the Gulf of Corinth and is forming nowadays below the Gulf of Corinth and the Peloponnese. Okay? And so this complex geometry was inherited from 35 million years of slab retreat. And you have to imagine that deforming the slab as we see it now implies a complex movement in the asthenosphere that surrounds this slab here. So the idea we have is that the slab retreat here causes the asthenospheric flow that we have here, and that this asthenospheric flow in turn controls the dynamics of back arc extension. So let's have a look to a numerical model of this. We are trying to model the effect of a slab tear. So we are seeing things from below, and you see the tear forming here. And you see this hole in the, where the asthenosphere can go through here. If we see the same thing from above, you see the slab retreat here, and the colors here represent the strain rate. So the more red it is, the more deformed it is. So if we look at this from the surface, from above, you can directly compare the velocity field that we have here with the GPS velocity field. So that's the data, that's the model. And the colors behind, so the strain rate, can be directly compared with the strain rate here calculated from the GPS velocity field here. And you see that the most active extensional area here in the western part of Turkey is found here, and that the equivalent of the North Anatolian fault here is found here. Okay. So we think we have captured somehow the mechanism that drives the deformation in that area, that's slab retreat mostly, and the slab tear that explain the strong localization of slab retreat on this narrow zone of the Hellenic slab. Okay. This is a view of the same sort of model, not exactly the same one, but from below, and you see the toroidal flow in the asthenosphere below the deforming back arc zone that is here. Okay. And if we look at the same model, but a vertical section in it, you see that the velocity along this vertical profile here, the velocity shows a very strong gradient in the lower continental crust here. Okay? And this is shown by the difference in the length of vector from here to here. So the lithosphere that is in the back arc region is sheared, and it is sheared with this sense of shear here that is compatible with the sense of shear we observe in most of the large-scale detachment that we have here. Okay. So we see that the flow of mantle related to slab retreat is able to control somehow the deformation in the back arc. So what about the larger scale mantle flow now? And we'll change scale and see things about Africa and Asia. So we saw this. You see here some motion path from 50 million years to the present, on top of the large low shear velocity province in the lower mantle here. We are at 2,800 kilometers here, one here and one here. And we have this high velocity domain here that could be the cemetery of slabs in the lower mantle. And what you see is that from 50 million years here, the continent and pieces of continent, they move from above this low velocity anomaly here, where we have the large plumes, all the way toward the zone of subducting material here, and of course the other sense here with the Pacific. Okay. So what is this? It is simply the large-scale convection that you see here between the low velocity province in the lower mantle, and the slab cemeteries here. Okay? In this paper by Becker and Facena in 2011, see that India is carried by this large-scale convection cell, and on the other side you have the Pacific convection cell. So can this have an importance in the deformation that we are studying? Let's start quickly with the AFR triple junction, with a few reconstructions from the Jurassic to the present. What you see in the Jurassic is that Apulia here is separating from Africa here and moving toward the north faster than Africa. Then in the lower Cretaceous, most of Africa is under extension. Okay? And extension prevails everywhere, even above the northern Tethys subduction zone here. In the late Cretaceous, we have a sort of accident where when most of the northern part of Africa, part of Apulia, and part of Western Europe are under compression, and this culminates with the abduction of the large ophiolitic naps like the Oman ophiolites here. And then extensions comes back. Okay? And until now, most of Africa is under extension here, and we have the separation of the Arabian plate from the African plate. And we have this motion here with the northward motion of Arabia, faster than the motion of Africa, and then the westward and southwestward motion of Anatolia and the Aegean. And this is very well shown on this figure here with the GPS velocity field. This is still active today. We see a very large-scale toroidal flow from the AFR here all the way to the Aegean. So how can we explain this? So one possibility is to look downward and to look in the mantle. And on this section here, it is almost north-south from South Africa to the AFR and Arabia, we see that the plume that is now active below Ethiopia is in fact deeply rooted in the lower mantle here. And this image suggests something like this, that the plume is moving upward and then northward here toward the north. Okay? And it is shown also by this S-wave tomography at 100 kilometers, the model of Scheffer and Lebedev, that is very useful. And you see that you have a connection between the hot regions here below the AFR across Arabia, the Middle East, and the eastern part of Turkey here, suggesting something like this. Okay. So the idea we have is quite simple in this paper published a few years ago, is that everything is driven by the displacement of the plume here that is moving northward and then turns toward the west or toward the east, and that this underlying flow here will drag the Arabian plate here and separate the Arabian plate from Africa. And then the flow will go down in the Hellenic subduction zone here. Okay. So if we focus now on the AFR here, and along this section here that was surveyed recently by colleagues here in this paper published 2 years ago, along this section, what is new is that most of the active and recent normal faults in that area, well, not so only recent, but since the Miocene in that area, they all deep toward the southwest. So the deformation in that area is very much asymmetric. And the idea is that this northward asthenospheric flow imposes a shearing deformation here and explaining the asymmetry that we see here. So the idea is that the long-term behavior is that Africa is above this large-scale convection cell here, and that the flowing mantle drags species of the continent toward the north. The first of these species was Apulia, and the last one is Arabia. And the accident I was talking about is here when the lithosphere the slab tries to penetrate in the lower mantle, and this puts the whole system under compression, and we have the abduction here. But most of my interest here is this part here. And this is not the only period when we see this. So we have seen Apulia, we have seen Arabia, and you see that 240 million years ago, or 400 million years ago, we already had blocks of the southern continents moving northward faster than the southern continents here, and crossing the Tethys and colliding with the northern continents here. So this pattern here is probably probably has a very long history, which is compatible with the postulated long history of plumes and convection here. Okay. So last thing, Philippe? Okay. The last thing is the formation of East Asia. Of course, it's a consequence, this has been known for a long time, of the collision with India, and also, which is not often taken into account, of the subduction of the Pacific and Indian oceanic lithosphere here. Okay? So you all know this very well. What's important is that we have here compression and crustal thickening here. That's very well known, the Himalayas and the Tibetan Plateau. We have extension and thinning in the whole eastern part of Asia, and not only the eastern part of Asia, but Southeast Asia as well. And we have backhog basins, such as the Japan Sea and the South China Sea, that open roughly at the same time in the Oligocene and the Miocene. Okay. So how can we connect this deformation here, compressional deformation, with the extension here? What sort of interaction can we think of between collision in the south, and backhog opening in the east? Okay. So that's an old reconstruction that I made in 1994, and you see the position, the present-day position in red, and the position at 45 MA here in this color here. And to explain this, there are different possibilities. So Taponi and others proposed their model of extrusion here. We proposed this model here, which is a bit different because extension here is a direct consequence of strike-slip faulting. And here, extension is imposed at the beginning of the experiment by the spreading of an unstable thick lithosphere here. Okay? But in none of these models do we have subduction. Okay? And subduction is here considered merely as providing a stress-free boundary to the east. Okay? But we know, of course, that extension is associated with slab retreat here, hence with mantle flow. Okay? So the question is, how does mantle flow underneath Asia? So let's have a look to this model here, Schaeffer and Lebedev model here. That's the kinematic trajectories that we have seen before, the white lines here, and the colored symbols here represent the fast direction of this S-wave seismic anisotropy. And when the symbols are in green, green means that they fit rather well the long-term trajectories. When they are red, they don't fit at all. So we see that if we look at 100 kilometers, so we are partly within the lithosphere here. What we see is this, of course, the motion of India toward the north, but we see this deformation here, suggesting this motion here toward the southeast. That's toward the retreating boundary here, and here as well. Okay. This is very similar to what Pietro Sternai obtained recently in a numerical model here. And you see the trajectories here are very similar to what is shown by the seismic anisotropy. If we go deeper, 200 kilometers, so below the lithosphere here, we still see this here that fits very well, or here. But as soon as we go into Asia, it doesn't fit at all, the direction of the trajectories. Okay? On the other side, we have the motion of the Pacific, of course. So we have, from here and here, a continuity of the asthenospheric flow, if we believe that this is asthenospheric flow, from India to the Pacific subduction zone. So this should have an impact on the behavior of slabs, of course, the slab below the Himalayas and the slab below Japan, for instance. So if we look at slab geometries, what do we see? So we see that the slab here below the Himalayas is overhanging here and detached, while below Japan, it is concave up. It is sitting on top of the transition zone here, or within the transition zone. So we see two reverse situations here. And one solution to explain that is that we have the Indian flow here, the flow carrying India here, that has reversed the slab here below the Himalayas. And here, the flow has followed the retreat of the Pacific slab here. So we have a complementary motion here toward the north and toward the east. Okay. If we go to Southeast Asia, the slabs are also overhanging, concave up, not overhanging, concave up to a certain stage, which is this profile here, where you see that the slab is cut in two parts here, and it's starting to get overhanging. And this point is just here. This is the anomaly, the slabs at 1,000 kilometers, and you see that they cross the trench right here, okay? So we have the Himalayan slab, which is overhanging, and we have the Sunda slab here that is concave up. So let's try to put this into perspective, and that's the large part of the Earth. That's the Pacific slab. That's the Philippine Sea plate, other smaller slabs, and that's the Indian slab that is overhanging below Southeast Asia here, and that is, overhanging here below the Himalayas and concave up here below Southeast Asia. And you see the transition from here to here is somewhere around here. The flow of the mantle is like this at 200 kilometers. So the flow is inverting the slabs here and following slab retreat here. At shallower depth in the lithosphere, we have this deformation and displacement here following the retreat of the Sunda trench here. And these are the main structures. Okay. So what's and I will finish on this, the idea is that the flow carrying India and originating from this big plume here is invading Asia here all the way to the Pacific subduction, something that is compatible with the geochemical anomalies in lavas of Asia. And what we have probably is this. So we see that the mantle flow inverts the slab here and follows the retreat of the slab here. So we have two things, the Indian mantle flow here, pushing everything to the northeast, and the Sunda trench retreat here, dragging the lithosphere toward the southeast and causing the extension that is shown in green here. Thank you.